Distinguishing accuracy and precision. 4 research teams measured the mass of a fossilized sauropod skull, and what each team wrote in the team notebook is shown in the table below. Suppose a later and more reliable measurement gives 7.1 kilograms for the mass of the same fossil. Decide which of the earlier measurements was the most accurate and which was the most precise. So let's take a look at a typical depiction of accuracy versus precision. Now, there may be criticisms of this analogy, but let's use it anyways because it's instructive. Imagine you have a dartboard and you are attempting to hit the center, the bullseye of the dartboard. And there are 2 throws. One is over here and one is over here. What we would claim is that the throw that hit the bullseye is more accurate than the one that was on the outside. It's closer to the intended target. And that's, in a sense, what accuracy is. Accuracy is the closeness of a measurement to the actual value. Now, it's an interesting thing because an actual value, there may not actually be an actual value, but there can be what we would call an accepted value. For example, we might claim that a foot is 12 inches. And if someone were to measure using a yardstick a foot and they came out with 11.5 inches, we would claim that their accuracy is off because a foot is by definition 12 inches. So for this problem, the accuracy question is quite simple. All we have to do is find the measurement given by the team, either A, B, C, or D, that is closest to the more reliable measurement. The more reliable measurement is 7.1 kilograms. So if you take a look at the 4 values, 6.9 plus or minus 0.2, what that means is, for team A, is that the measurement is anywhere from 6.9 up to 7.1, all the way down to 6.7, plus or minus 0.2. But the average value, the value that's given, is 6.9. So the question then is, how close is 6.9 to 7.1? Well, it's off by 0.2, right? That's the difference. So now let's try team B. Team B just gives one value. It says that it's 6.7. Well, compared to 7.1, that's off by 0.4. We would claim that that is less accurate than measurement A, or Team A's measurements, which was 0.2. Now let's try Team C. Team C goes anywhere between 7.18 and 7.22. Now, in between that is 7.20, right? So we might claim that this one is 7.20 plus or minus 0.02, right? 0.02 is, if you subtract that, you get 7.18, and if you add 0.02, you get 7.22. So this one, 7.20, is still off a little bit. It's 0.1 off, right? Because again, we're comparing it to 7.1. And then D is 7.50 plus or minus 0.50%. Now that's a little tricky. 0.50% of 7.50 kilograms. So let's figure out what that is. 0.5% is 0.5 over 100, right? That's what a percent is. It's a number divided by 100. Okay? So times 7.50 kilograms. Okay, so let's figure out what that is. 7.50 times 0.5 over 100 is 0.0375. So the value that we would actually report here would be 7.50 kilograms plus or minus 0.0375 kilograms. Okay, so now we ask how close is 7.5 to 7.1? It's off by quite a bit, right? It's off by 0.4. So this one actually has the smallest difference. That's the one that's closest to 7.1. So we would claim that C is the most accurate. And we would claim that D is the least accurate. Okay, does that make sense? It's the closeness to the actual or the accepted value. Okay, 0.2, 0.4, 0.1, 0.4. Actually, I just noticed B is off by 0.4 as well. So it's B and D are the least accurate. Okay, now let's talk about precision. Precision is often discussed in terms of repeatability. But again, let me show you this analogy. Again, there may be problems with this analogy, but we don't need to get into the details of that. Suppose I'm going to use X's to represent 3 throws. So I throw 3 darts and that's where they show up. Okay? Now suppose, let me make it a little bit bigger. Suppose I do it 3 more times, and I'm going to use little squares to represent these 3s. The question is, how close are those 3 throws to each other? So in other words, like if you look at these 3, they're pretty far apart from each other, right? Whereas these are very close. We would say these are more precise measurements. They're closer to each other. It's an internal comparison as opposed to comparing it to a standard. So you need to know that 7.1 kilograms was the actual value to find the accuracy in the first part of this. But you don't need to know what the actual value is to look at precision. To look at precision, you just look how close they are to each other. Okay, so if I had 3 numbers, 5, 5.1, 4.9, versus 5, 5.3, 4.7, we would claim that these are more precise because they're closer to each other. So again, you're not comparing them to an external standard. We're not claiming that, hey, we know the actual value is 5, so this is either closer or further. You need that for accuracy, but for precision, it's just how close they are to each other. So here's what happens. The plus or minus is used as a way of reporting precision. So if I have plus or minus 0.01 versus plus or minus 0.02, this would be more precise. Because it's saying that, look, we know the range this is within, and the range doesn't vary by very much. The range varies by plus or minus 0.01. And that's a smaller range, sort of like here. That's a smaller range than if the difference is 0.02. Okay, plus or minus 0.02. So let's take a look at precision then. So looking at these values, if you look at A, the plus or minus is 0.2. I won't put the units in, we don't need those. For B, they don't give you a plus or minus, they just say it's 6.7. So in a sense, they're saying plus or minus 0. That's really what they're saying. They're saying it has no error in it. Or at least the error is so small we can ignore it. For the second one, it's plus or minus, for this third one, C, it's plus or minus 0.02. Now you might ask, how do you get 0.02 for C? Well, it's between 7.18 and 7.20. So what you do is you find the midpoint between them. So you take your 7.18 and your 7.22 and you ask, where's the midpoint? The midpoint is 7.20. So this is plus 0.02 and this is minus 0.02. So there's your plus or minus 0.02. So for C, it's plus or minus 0.02. Now that's actually pretty small, right? That's a lot smaller than 0.2. That's 90% smaller, but it's still bigger than 0, right? And then D, we have to be careful. With D, it's 0.5%. So I think we figured out 0.5% is right here, 0.0375. I already did that. So this is plus or minus 0.0375. So looking at these, this one is the most precise. And it looks like 0.03, this one's the least precise, right? So one of the things that people have difficulty with this problem, I hope now you understand the difference between accuracy and precision, is that part D, the part D where it gives you the percentage. So what they're saying is it's 0.5% of 7.50 kilograms. So 0.5% is 0.5 over 100 of 7.5 kilograms means times 7.5 kilograms. And then that's going to give you your plus or minus, which is, it's often referred to as the experimental error. The values after the plus or minus are often referred to as experimental error, meaning how precise are these measurements. But really, error has two concepts. One is accuracy, how close you are to the true value, the actual value, and then precision, how closely related are your measurements to each other. And they are related, and our analogy here of the dartboard isn't perfect because it sort of decouples those two relations, but for us that's fine.